So today we're going to talk about wireless LAN concepts. So a wireless LAN is a type of wireless network that is commonly used in homes, offices, and campus environments. They make mobility possible within the home and the business environment. The wireless infrastructures adapt to rapidly changing needs and technologies, and they help with the cost of implementing a network because you save costs on wiring or the lack thereof, and having to run many wires through a wall, through your home, through your business. So there are different types of wireless networks that you should be familiar with. First one is your wireless personal area network, or a WAN. This is a low power, short range type of network, and it'll span from 20 to 30 feet or 6 to 9 meters. It is based on the IEEE 802.15 standard, and it operates at 2.4 gigahertz. So examples of WAN are both your Bluetooth and your Zigbee networks. Now your wireless LAN is for medium-sized networks up to about 300 feet. They are based on the IEEE 802.11 standard, and they are capable of running in frequencies of 2.4 or 5.0. Then you have your WAN. Your WAN will cover a large geographic area such as a city or a district, and it uses specific licensed frequencies in order to gain their wireless connectivity. And then you have a wireless WAN, which is a very extensive geographic area for national or global communication, and again, utilizing specific licensed frequencies for their purposes. So Bluetooth, IEEE WAN standard, is used for device pairing at up to 300 feet or 100 meters. Most of you, I'm sure, are very familiar with Bluetooth. Everything today is pretty much Bluetooth based. So it is used to connect cell phones, vehicles, etc. Bluetooth Low Energy, or BLE, supports mesh topologies to large-scale network devices. Bluetooth Basic Rate Enhanced Rate supports point-to-point topologies and is optimized for audio streaming. WiMAX is a worldwide interoperability for microwave access, so it is an alternative to broadband wired internet connections. It is identified through the standard of IEEE 802.16, and it goes for up to 30 miles or 50 kilometers. It may supply an entire small village or a community. I don't know if you've ever seen anything like it, though, but I watched a video many, many years ago, or actually it was someone who came here to present, and they had this massive, it almost looked like, if you're familiar with what the organ looks like in a church, it was massive and big like that, and just had these very large tubes with antennas in it, and it was on the side of a building, and it was, I wish I could remember the video so I could show it to you, but I cannot. But I think that was my first realization to how expansive wireless has become. Now, cellular broadband can carry both voice and data. It is used by your phones, your automobiles, your tablets, and laptops, all in order to connect to a data network. So your Global System of Mobile, GSM, is internationally recognized. Code Division Multiple Access, CDMA, is primarily used in the United States. Now, satellite broadband is going to use directional satellite dishes aligned with satellite in geostationary orbit. So it needs a clear line of sight. There can be no trees, houses, buildings, etc. Typically used in rural locations where cable and DSL are not an option, such as in a cornfield on a farm, where it would be a feasible solution. It would not be a feasible solution to run cabling. So here are your 802.1 standards. So the standard itself is defined as 802.11. These standards define how radio frequencies are used for wireless links. What you need to gain from this and what you want to take away from this is you have to understand the standard itself, the data rates that it works at, and the radio frequency that it works at. So 802.11 itself has a radio frequency of 2.4 gigahertz with data rates up to 2 megabits. 802.11a, so you're going to see all these different letters now after 802.11. So these are all enhanced versions thereof. And so what you have to kind of pay attention to is some of them are backward compatible and some of them are not. So if you're trying to build something and have everything in your organization interoperable, you have to pay attention to those that are compatible together and backward compatible. 802.11a runs at 5 gigahertz, data rates up to 54 megabits, not interoperable with 802.11b or 802.11g. 802.11b, 2.4 gigahertz radio frequency, developed prior to 802.11a. It has data rates up to 11 megabytes. It has a longer range than 802.11a and is better able to penetrate building structures. Then you have 802.11g, also running at 2.4 gigahertz, with here data rates up to 54 megabits per second. It is backward compatible with 802.11b. 802.11n. Can run at both 2.4 and 5 gigahertz. Data rates between 150 and 600 megabits. This one is going to require multiple antennas with MIMO technology. So we're going to talk a little bit about antennas and stuff as we go further along. 802.11c is in the 5 gigahertz range. It has data rates from 450 megabits per second to 1.3 gigabits. It supports up to 8 different antennas. And then you have 802.11ax running at both frequencies of 2.4 and 5 gigahertz. This is high efficiency wireless, or HEW, capable of using 1 gigahertz and 7 gigahertz frequencies. Now, when you're thinking about radio frequencies, all wireless devices operate in the range of the electromagnetic spectrum, as you see here. I always like to include this picture because when we think about things like just in just everyday chatting, when you get an X-ray, gamma rays, laser, infrared, what does all that mean? Well, they are actually defined in the electromagnetic spectrum. And so take a really good look at this chart, and it's kind of a really groovy chart. And it actually breaks out and tells you at what ranges different things are happening. So WLAN networks operate in the 2.4 and 5 gigahertz frequency bands. 2.4 operates in the ultra-high frequency, or the UHF range. It includes 802.11, B, G, N, and AX. The 5 gigahertz operates in the super high frequency, or SHF range, and it includes 802.11a, N, AC, and AX. Now, there are 3 main organizations that implement standards to ensure interoperability between devices that are made by different manufacturers. Internationally, the 3 organizations influencing WLAN standards are the International Telecommunications Union, the ITU. This is going to regulate the allocation of radio spectrum and satellite orbits. Then you have IEEE, the Institute of Electrical and Electronic Engineers. This is going to specify how a radio frequency is modulated to carry information. It also maintains the standards for local and metropolitan area networks with IEEE 802 LAN and MAN family of standards. Wi-Fi Alliance promotes the growth and acceptance of WLANs. It is an association of vendors whose main objective is to improve the interoperability of products that are based on the 802.11 standard. Now again, in talking about that electromagnetic spectrum, and I think I mentioned this in class before, What people don't realize is when you're listening to the radio and you're listening to 92 Pro FM, 92 is a frequency on that spectrum. Okay, so just like, you want to think about it, it's assigned to you, just like as if you were to purchase an IP address or something of that nature. That is your frequency. 95.5, that is the frequency that used to be BRU. I think it's a religious station now. So all of your radio stations, whether they're AM or FM, are radio frequencies. Now, when you need wireless connectivity, you need a wireless NIC in order to get you that. Now, prior to today's world, where everything is pretty much embedded in your devices, your devices today come with both wired and wireless capabilities. In the older days, it wasn't like that. So in the olden days, a device needed to have some sort of antenna to connect to the wireless LAN. To communicate wirelessly, laptops, tablets, smartphones, and even the latest automobiles included integrated wireless NICs that incorporated radio transmitter and receiver. Now, if a device does not have an integrated wireless NIC, then a USB wireless adapter can be used, as shown in the picture. There are many, many different types of wireless adapters that can be utilized. This is an example, and what you see different from having just a WAN connection is you see the actual antenna that you need for the signal. And again, nowadays, as I said, if you were to crack open your laptop, you would see a tiny little chip with two little leads coming off of it, one for transmitting and one for receiving. That is your wireless NIC card embedded in your device. Now, your wireless home router typically interconnects wireless devices using a small, your home typically interconnects wireless devices using a small wireless router. So wireless routers serve as the following. They are an access point, so they're going to provide your wireless access. They are a switch, so you use them to interconnect wired devices, as you see here on the back of this, looking at the ports. And they are also a router. So they provide a default gateway to other networks and to the internet. It is very similar to a multi-layer switch. So most of your home wireless routers, or just wireless or not, your home routers today are IRS routers, which is integrated routing services, meaning you have the uplink, you have switch ports, you have Ethernet, you have everything that you need embedded in that one device. Now, wireless clients use their wireless NIC to discover nearby access points. Clients then attempt to associate and authenticate with that access point. After being authenticated, wireless users have the access to the network resources. So as shown here in this picture, Cisco has a Cisco Meraki Go AP. These are managed via the internet. So there are many, many different types of wireless access points out there. Of course, Cisco has to plug Cisco. So AP categories, they can be categorized as either autonomous APs or controller-based APs. So an autonomous AP is a standalone device. It is configured through a command line interface or a GUI. Each autonomous system AP is going to act independently of the others and is configured and managed manually by you, the administrator. This type of network is very difficult to manage because every AP would have to be adjusted with regard to power, frequency, securities, etc. So this particular area or realm or category is more labor intensive on the administrator because you control everything within those standalone devices. Now, controller-based APs, also known as lightweight APs or LAPs, use lightweight access point protocol to communicate with a LAN controller or WLC, which may or may not be on the same network as that AP. but the AP must be able to contact the WLC. So now each LP is automatically configured and managed by the wireless link controller. So we would go in there and we would configure the wireless link controller, and then that wireless link controller would push everything out to the APs. So both of these APs physically look the same. However, it is the iOS that determines whether they are autonomous or lightweight. Now there are different types of antennas. The type of antenna depends on the scenario of the network that's being utilized. So omnidirectional. This is going to provide 360-degree coverage, ideal in houses, offices, hotels, etc. Directional is going to focus that radio signal in one specific direction, such as in a point-to-point network. Examples of these are the Yagi and the parabolic dish. And then you have multiple input, multiple output, or MIMO. These use multiple antennas, as you see here, similar to what I was describing to you in my story, except the one I was describing was much larger. Held up to 8 antennas to increase bandwidth. So the one I saw probably was not a MIMO, but it was something similar that was just outstandingly huge. If I can find it, I will upload it to you. Now, in ad hoc mode, so different topology modes. In ad hoc mode, it is used to connect clients in a peer-to-peer manner without an AP. So this is one way that a threat actor can gain your information. They can set themselves up as an AP, and all of your information would then stream right to them or right through them. Then you have infrastructure mode. This is used to connect clients to the network using an AP. Then you have tethering. Tethering is a variation of the ad hoc topology, and it is used when a smartphone or a tablet with a cellular database or data access is enabled to create a personal hotspot, which I'm sure some of you have done thus far with your cell phones. So that was quite prevalent, actually, with tethering with your cell phone and using your cell phone as a hotspot. I know when COVID happened and everybody was jammed up in trying to get a VPN back to the college, and I was actually utilizing at the time, I was searching. It was just all in the timing. I just happened to be looking for a new internet provider. And I had canceled my subscription because it just got too costly and too crazy, and I was without the internet, and then COVID happened, and I had to find a way to teach from home. So it was quite costly because every time you use your phone as a tether and as a hotspot, you're paying for that service, and it is not cheap. So do understand that it is an option if you are absolutely somewhere where you cannot gain access. You can go through your cell phone and use that as a hotspot to gain access. Now, infrastructure modes define 2 different topology blocks. You have your basic service set. It uses a single AP to interconnect all associated wireless clients, so this is similar to a home network environment. Clients in different BSSs cannot communicate with one another. They are totally separate networks. However, you do have an extended service set, an ESS. An ESS is a union of 2 or more BSSs, interconnected by a wired distribution system. So clients in each BSS can communicate through the ESS itself. So now your frame structure. So your 802.11 frame is similar to your Ethernet frame, except that it contains more fields to address the different types of controls we need in a wireless scenario. So your header has a lot more information, as you see here, okay? I can get my mouse over here. Okay, you have your frame control, duration, your address 123, your sequence control. So all of these are in the header of a wireless. Okay, then again, you have your payload, and then you have your frame check sequence field. So what is really being altered is all the information in a typical header frame. So WLANs are half duplex, and a client cannot hear while it is sending, making it impossible to detect a collision. So thinking back to when we talked about our different media access methods, WLANs use carrier sense multiple access with collision avoidance to determine how and when to send the data. So a wireless client does the following. It listens to the channel to see if it is idle, meaning there is no other traffic it can currently detect on that channel. It sends a ready to send, an RTS message, to the AP to request dedicated access to the network. It receives a clear to send, a CTS message from the AP granting access to send. It waits a random amount of time before restarting the process if no CTS message is received. If one is received, it transmits the data. Now thinking back to when we talked about CSMACA, when it sends out that request, it also sends out the amount of time that it is going to utilize the wireless environment. Therefore, that is the avoidance portion of the CSMACA. Okay, so I'm requesting the network, I'm requesting to utilize the network, and I'm telling you how long I'm going to need that network so that no one else should transmit at that time. So acknowledges all transmissions. If a wireless client does not receive an acknowledgement, it assumes a collision occurred, and it then restarts that request process all over again. So for wireless devices to communicate over a network, they must first associate with an AP or a wireless router. Wireless devices complete the following three-stage process. They have to discover an AP, if there is one available. If so, then the device will authenticate with the AP. If authentication is granted, then the device will associate with the AP. So to achieve successful association, a wireless client and an AP must agree on specific parameters. The SSID, the client needs to know the name of the network to connect. The password, this is required for the client to authenticate to the AP. The network mode, so whichever 802.11 standard is in use. The security mode, so the security parameter settings that are on the AP, and you can choose from WEP, WPA, or WPA2. Channel settings, which frequency bands are in use. Most common ones are 1, 5, and 11. So which ones are being utilized? So all of those parameters have to match before association can happen. You will learn about WPA, WEP, WPA in Cisco 3. Now you have passive and active discover mode. So wireless clients connect to APs using a passive or active scanning probing process. In passive mode, the AP openly advertises its service by periodically sending out broadcast beacon frames containing its SSID, supported standards, and its security settings. Active mode, wireless clients must know the name of the SSID. The wireless client initiates the process by broadcasting a probe request on multiple channels. So the first one in the passive mode Sometimes this can be problematic. It can open up areas for threat actors because you are openly sending out, broadcasting your information, your network's name, your supported standards, your security settings, okay? So be aware of that in your home devices as well, okay? If you're utilizing your home router and you haven't done anything to it, chances are when you go into it, if you either you can browse into it utilizing the IP address on the back of your router, or you can console into it. It does have a console port that you can physically plug into if you have a laptop capable of doing so. And if you look at it, chances are your SSID is default. So you want to change that. And you probably want to take off this broadcasting mode. And you want to put at least some security. WPA2 is the better one. So if you haven't done that already, you might want to take a look at that and consider doing that to your home device. Now, CAPWAP, Control and Provisioning of Wireless Access Point, is an IEEE standard protocol that enables a wireless LAN controller to manage multiple APs and WLANs. So it is based on a lightweight access point protocol, which is a protocol that can control multiple Wi-Fi wireless access points all at once, but adds additional security with datagram transport layer security. So it encapsulates and forwards WLAN client traffic between an AP and a wireless LAN controller over tunnels using ports 5246 and 5247. It also operates over both IP4 and IP6. IP4 will use IP protocol 17, and IP6 will use IP protocol 136. So the CAPWAP split MAC concept does all the functions normally performed by individual APs and then distributes them between two functional components, the AP MAC function and the WLC MAC function. Within your AP function, beacons and probe responses, packet acknowledgements and retransmissions, frame queuing and packet prioritization, MAC layer data encryption and decryption. Now, the heavier part of gaining access to an AP is done by your wireless LAN controller. Authentication, association and reassociation of roaming clients, frame translation to other protocols, and then termination of 802.11 traffic on a wired interface. So, DTLS encryption. Datagram transport layer security provides security between the AP and the wireless controller. It is enabled by default to secure the CAPWAP control channel and encrypt all management and control traffic between the AP and the wireless controller. Data encryption is disabled by default and requires a DTLS license to be installed on the controller before it can be enabled on the AP. So by default, you would have to control encryption, but not, you would have control encryption, but not data encryption. So FlexConnect enables the configuration and control of APs over a WAN link. The WLC need not be on the same LAN, but must be reachable by those APs. So as you see here in this diagram, I have a branch office stemming off my corporate office. My WLC is in my corporate office. In my branch office, I'm using a FlexConnect AP. So there are two modes of options for the FlexConnect. Connected mode. In connected mode, the WLC is reachable. The FlexConnect AP has CAPWAP connectivity with the WLC through the CAPWAP tunnel. The WLC will perform all the CAPWAP functions. Then you have standalone mode, where the WLC is unreachable. So the FlexConnect AP has lost CAPWAC connectivity with the WLC. The FlexConnect can assume some of the WLC functions, such as switching client data locally and performing client authentication locally. So, if the demand for a specific wireless channel is too high, the channel may become oversaturated, degrading the quality of the communication. So channel saturation can be mitigated using techniques that use the channels more efficiently. So you have direct sequence spread spectrum, DSSS. It is a modulation technique designed to spread a signal over a larger frequency band. It is used by 802.11b to avoid interference from other devices using the same 2.4 gigahertz frequency. Some devices are home devices, such as your wireless phones. Then you have the frequency hopping spectrum. This is going to transmit radio signals by rapidly switching a carrier signal among the many frequency channels. Sender and receiver must be synchronized to know which channel to jump to. It is used by the original 802.11 standard. Then you have the orthogonal frequency division multiplexing. This is a subset of frequency division multiplexing, in which a single channel uses multiple subchannels on an adjacent frequency. OFDM is used by a number of communication systems, including 802.11, AG, N, and AC. So your channel selection. The 2.4 gigahertz band is subdivided into multiple channels. Each is allotted 22 megahertz bands and separated from the next channel by 5 megahertz. So a best practice for 802.11 BG and N requiring multiple APs is to use non-overlapping channels such as 1, 6, and 11 shown in orange. This is going to allow overlap in a cellular structure. Multiple channels as 1, 6, and 11, and I do apologize, I think I said 1, 5, and 11 previously, 1, 6, and 11, and if the need arises for additional areas to be covered, additional APs can be configured to increase the coverage area. This is typically what you would see in a commercial wireless system. Okay, so you see the overlapping in these diagrams that I have put here for you. So what happens in a site survey, a wireless company comes in and they pretty much do this functionality and they walk through and they see where they can gain this overlapping, okay? So there's overlapping with channels. So the idea is when you have overlapping in your channels, that a signal should never be lost from point A to point B, or as you're walking through a corridor or wherever you happen to be. In the beginning, when CCRI first had wireless communication, you would walk down the hall, have it, go through the corridor, lose it, get to the other side of the corridor, gain it. So it was very sketchy in the beginning until it was really honed in. Wireless in the beginning was very sketchy. There are so many things now that you can do to improve it with the different antennas and this overlapping scenario and things of this nature, but still, big security risk. So for the 5 gigahertz standards, 802.11a, N, and AC, there are 24 channels available. Each channel here is separated from the next by 20 megahertz. Non-overlapping channels here are 36, 48, and 60. And just by looking at the diagram, you can kind of see. Now, how you plan a WLAN development? Again, the number of users supported by WLAN depends on the following: the geographical layout of the facility, the number of bodies and devices that can fit into a space, the data rate that the user expects, and the use of non-overlapping channels by multiple APs, and transmitting power settings. So when you are planning the location of your APs, the approximate circular coverage area is important, as well as other environmental elements. So in WLAN, WLAN is open to anyone with within range of an AP and the appropriate credentials to associate to it. Attacks can be generated by outsiders, disgruntled employees, and even unintentionally by perfect employees. Wireless networks are specifically susceptible to several threats, including the following: interception of data. Interception attacks allow unauthorized users to access our data, applications, or environments, and are primarily an attack against confidentiality. Wireless intruders are unauthorized users gaining access. Again, denial of service attacks, which you are very familiar with, denying viable users services that they would need. And then a rogue AP. This is a device not sanctioned by an administrator, but is operating on the network. This could be an access point set up by an intruder. It provides a wireless backdoor channel into the private network for outsiders. So it can bypass network firewalls and other security devices and open a network to attacks. So wireless DOS attacks can be the result of the following: improperly configured devices, a malicious user intentionally interfering with the wireless communication, and accidental interference. To minimize the risk of a DOS attack due to improperly configured devices and malicious attacks, you need to harden all your devices. You need to keep passwords secure. You need to create backups. And you need to ensure that all configuration changes are incorporated off hours. You never want to do anything drastic during production time. Now, a rogue AP is an AP or a wireless router that has been connected to a corporate network without explicit authorization and against corporate policy. Again, thinking back to what I talked about the other day in class, where if you have this out in the open, a racking system out in the open, someone could potentially walk in and plug into it, therefore creating a rogue AP. So once connected, that rogue AP can be used by an attacker to capture MAC addresses, data packets, gain access to your network resources, or to even launch a man-in-the-middle attack. A personal network hotspot could also be used as a rogue AP. So a user with secure network access enables their authorized Windows host to become a Wi-Fi AP. To prevent the installation of your rogue APs, organizations must configure your wireless link controllers with rogue AP policies. You also need to be using some type of monitoring software to actively monitor the radio spectrum for unauthorized APs. Now, the man-in-the-middle attack. This is a hacker that has positioned themselves in between two legitimate entities in order to read or modify the data that passes between the two parties. A proper wireless MITM attack is called the evil twin AP attack, where an attacker introduces a rogue AP and configures it with the same SSID as the legitimate one. Defeating a man-in-the-middle attack begins with identifying legitimate devices on your WLAN. To do this, your users need to be authenticated. After all of the legitimate devices are known, the network can be monitored for abnormal devices or traffic. This can sometimes be more difficult than it sounds and may take a long period of time to implement. Now, SSID cloaking and MAC address filtering. To address the threats of keeping wireless intruders out and protecting our data, two early security features were used and are still available on most routers and APs. SSID cloaking. APs and some wireless routers will allow the SSID beacon frame to be disabled. Wireless clients must be manually configured with the SSID in order to connect to that network. MAC address filtering. An administrator can manually permit or deny clients wireless access based on their physical MAC address. So the router is configured to permit 2 MAC addresses. Devices with different MAC addresses will not be able to join the 2.4 gigahertz WLAN. This is a good solution to use for home networks. Now, the best way to secure a wireless network is to use authentication and encryption systems. 2 types of authentications were introduced in the 802.11 standard. Open system authentication, where no password is required. Typically used to provide free internet access in public areas like cafes, airports, and hotels. The client themselves is responsible for providing security, such as through a VPN. Then you have your shared key authentication. These provide mechanisms such as WEP, WPA, WPA2, and WPA3 to authenticate and encrypt data between a wireless client and the AP. The password, however, must be pre-shared between both parties to connect. WEP is no longer an acceptable method of authentication, as it is easily cracked. Now, there are currently 4 shared key authentication techniques available. You have the wired equivalent privacy, or WEP. The original 802.11 specification, it was designed to secure the data using the Revis cipher encryption method with a static key. It is no longer recommended and should never be used. Then you have Wi-Fi protected access, a Wi-Fi alliance standard that uses WEP but secures the data with a much stronger temporal key integrity protocol, or TKIP, encryption algorithm. TKIP is going to change the key for each packet, making it much more difficult to hack. Then you have WPA2. It's going to use the Advanced Encryption Standard, or the AES, for encryption. AES is currently considered the strongest encryption protocol. Then you have WPA3. This is the next generation of Wi-Fi security. All WPA3 enabled devices use the latest security methods, disallow outdated legacy protocols, and require the use of protected management frames. So all of these security methods you are going to learn in Cisco 3. And what you want to take apart is, it is not just choosing one over the other. When you are protecting your data, it is a step-through process where you decide on an encryption, you decide on a hashing method, you decide on a key method, and it kind of all gets bundled together. So have a basic understanding of what these are here, but when you get to Cisco 3, you're going to learn how it is an actual laid upon effect to be secure. Now, authenticating a home user, home routers typically have 2 choices for authentication, WPA and WPA2, with WPA2 having 2 authentication methods. Personal, which is intended for home or small office. Users will authenticate using a pre-shared key, or a PSK. Wireless clients will authenticate with the router using that pre-shared key, or pre-shared password. No special authentication server is required. Then you have the enterprise. This is intended for enterprise networks. It is going to require a remote authentication dial-in user service, or a radius authentication server. The device must be authenticated by the radius server, and then the users must authenticate using 802.1x, which uses the extensible authentication protocol of EAP for authentication. So again, all of these keys, you will start to get an introduction to all these different methods in Cisco 3. And then in the network security course, you'll really get into how all these different things work. Unless, of course, they've changed the course since I've taught it. Now, WPA and WPA2 include 2 encryption protocols. So again, this is that building upon effect I'm talking about here. You have the Temporal Key Integrity Protocol, or TKIP. This is used by WPA, and it provides support for legacy WLAN equipment. It makes use of web, but encrypts layer 2 payload using that TCAP. Then you have Advanced Encryption Standard, AES, used by WPA2. And this uses the counter cipher mode with blockchaining message authentication code. This is going to allow destination hosts to recognize if the encrypted and non-encrypted bits have been altered. Authentication methods. Enterprise security mode, used mostly for corporate, requires an authentication, authorization, and in counting EEE radius server. There are 3 pieces of information that are required: the radius server IP address, the UDP port that supports radius, which is port 1812 for authentication, and 1813 for accounting, but can also be utilized using 1645 and 1646. And then you need a shared key. The shared key is used to authenticate the AP with the radius server. User authentication and authorization is handled by the 802.1x standard, which provides a centralized server-based authentication of the end users. WPA3, because WPA2 is no longer considered secure, 3 is recommended when available. It includes 4 features. WPA3 Personal. This thwarts brute force attacks by using simultaneous authentication equals SAE, which is a password-based authentication and password authenticated key agreement method. WPA3 is Enterprise. It is going to use that 802.1x in the EAP authentication. It does require the use of 192-bit encryption, cryptographic suite, and eliminates the mixing of security protocols for previous 802.11 standards. Open networks do not use any authentication. However, they use opportunistic wireless encryption, which is a Wi-Fi standard that ensures that communication between a public hotspot and an end device is protected from each other, is protected from other end devices by encrypting all the wireless traffic. And then you have IoT, the Internet of Things onboarding. This uses device provisioning protocol to quickly onboard IoT devices. So there's a lot of information about wireless technology, not a lot of good examples here. I will look to some videos to give you some examples so you understand a little bit more. Do understand, however, though, that wireless is open air, therefore it is a security risk. Therefore, you are going to learn about those different hashing methods, security methods, keys, all the things that we want to implement in order to gain the most secure network that we possibly can gain.